Okay, now that we've learned a ton about probability back in Chapter 5, and now we've learned a little bit about random variables, we could kind of put everything together to help us understand a combination of probability and random variables. And what we're going to do is there's two very famous probability models that we're going to use. One very famous model we use is the normal model, but there's two other very famous models out there, and we're going to learn about one of them in this video and one in another video. This one is called the binomial probability model. Now, the binomial probability model is a very specific probability model. So let me write that down. This is a specific probability model. And like any probability model, we're trying to find probabilities of certain things occurring. And again, it's a random event. It's a random variable, meaning that we're not quite sure what could happen. But the binomial model is, again, very specific. So there are a couple conditions that have to be met for a binomial model to be used. And there are 4 conditions that we're going to talk about. And as we do every problem today in this video, we're going to make sure that we meet these 4 conditions. And the way to remember these 4 conditions is to remember your bins. B-I-N-S. We'll say remember your bins, and it also kind of makes sense for binomial bins, your binomials, B-I-N for bins, and then you get my point for binomial model. So the I stands for, I'm sorry, let's start with the B. The B stands for that the model must be binary. And if you know anything about the word binary, the word binary means 2. Okay, so there's only 2 possible outcomes. So 2 possible outcomes for a trial. And we label those very simply. P is success, and Q is failure. So every trial is either going to have success or failure. So when a trial is done, we're going to say, "Ooh, that was successful," or "Ooh, that was a failure." There's nothing else. There's no other outcomes. That's why we call it binary, or that's also where we get the binomial from. 2 possible outcomes, success or failure. We'll say P is success, Q is failure. If you know P, Q could be found by doing 1 minus P. So obviously, if you know success is, say, 30%, then failure would be 1 minus 30%, or 100 minus 30%, or 70%. Okay, I stands for independent. The trials must be independent. And we hopefully by now knows what that means. That means that the result of one trial will not affect the result of the next. Okay, so for example, if we're picking cards out of a deck of cards and we take one out and we look at it and we keep it, well, that means when we reach in the second time, the probability is going to change, right? So the trials are not independent. So we need the trials to be independent. We need the result of one trial to not affect the result of the next trial. So that's what we need to say by I for independent. The N is for the number of trials. So the number of trials is N. So in each binomial problem, you must be given a specific number of trials. So I use the N for the number, N for number, and the number of trials must be N, meaning you must be given a specific number of trials. It's a fixed number of trials. So you will be told a specific number of trials that you need to examine, and that needs to be true for any binary problem. So the last thing is the S, and the S stands for the same. And what we mean is that we need the probability of success to stay the same on every trial. So the probability of success must stay the same for each trial. So if we establish from the beginning that the probability of success is 20% or 0.2, it needs to stay that chance every single time. Okay? We've seen problems where the chance of success changes. Let's say we're trying to get a blue sock out of a drawer of 10 socks, and we take one out, and well, now there's 9 socks, and we already got a blue one, and now we're trying to get another blue one, so now there's 9 socks and 1 less blue sock. See, that's where the probability of success for a blue sock changes. We cannot allow that to happen for a binary model. So let's review the bins real quick. The first one is it must be binary, which means you must have a specific two outcomes, success or failure. I stands for independent. The trials must be independent of each other. N stands for the number of trials is N. There is a specific number of trials given to you. We call that N. And S stands for the successes must stay the same. So successes stay the same. Chance of success stays the same. And this is what we mean when we talk about a binary model. Now, the last thing I really want to emphasize is what is the X? Remember, we talked about random variables X, right? Random variable X means we're trying to find our specific outcome. So when we do a binary model, what is it that we're looking for? So we're looking for X successes in N trials. And this actually, if you understand this right here, that the random variable X is the number of successes in N trials, it actually all makes sense. So we need a specific number of trials. That's number 3 here. We need our chance of success to stay the same throughout. That's number 4 here. And we must have, there only be 2 options, success and failure for any given trial, and that's number 1 here. And then we also must make sure that those trials are independent of each other. So when we think about when we think about binomial probability models, we're always thinking about how many successes can we have out of N trials. So now we're going to look at an example here, and I hope it all ties together. I really hope so. Okay, doctors claim that 25% of children have type O blood. If 5 children are selected at random, let the random variable X be how many have type O blood. So let's try to make sense of this. Okay, first off, success is O blood. And I don't want to look at like a 0, so I'm going to say type O blood. That's success. And that would be 0.25. And anything else would be a failure. That would be Q, 1 minus 0.25. That would be 0.75. So our first condition is checked. This is binary. It's either going to be type O blood or not. Success or failure. 25% chance of type O blood, 75% chance it's not type O blood. So that is checked. That's very good. The second needs to be independent, which means that if one kid has type O blood, it cannot affect the next kid. Now, if we're talking about a family of 5 brothers here, well, we might have an issue because 5 brothers might genetically all have the same blood. But as long as we're selecting students or children at random here, not 5 brothers, that wouldn't be random, we can't expect to have the trials to be independent of each other. Next up, we need to have a certain number of trials, and it did stay. We're looking at 5 children. So we do have a set number of trials. We're looking at 5 children. And lastly, we need the chance of success to stay the same. So just because the first 2 kids have type O blood, it doesn't make the third kid any more or less likely to have type O blood. It stays 25% the whole time. So this is what we're talking about. We're talking about a binomial problem. We're given a chance of success, 25%, and we're given a set number of trials. So now let's think about the random variable X, right? What could happen? Well, in a binomial model, which we do have now, we could have anywhere from 0 successes to 5 successes. Now, that's because I'm only looking at 5 kids. And then anything in between is possible. So I could have 1 success, I could have 2 successes, I could have 3 successes, I could have 4 successes. So a binomial model, you could have anywhere from 0 to N successes. In our case, N is 5, so I have 0 successes, 1, 2, 3, 4, 5. So this would be my very easy probability model. And now I need the probabilities. And this is where things get tricky. This first one, no successes, is very, very simple. Everybody understands no successes. That is very, very easy. This would be 0.75 to the 5th. All failures. A failure and a failure and a failure and a failure and a failure. That's very easy. The other one to understand that's very simple is all 5 successes. This would be 0.25 to the 5th. All 5 successful. Success and success and success and success and success. It's these options in the middle that are actually a little bit tricky to figure out. Let's explain this. Let's talk about 1 success. So if I have 1, 2, 3, 4, 5 kids, and I need one of them to be successful. Well, it could be any one of them. Now, I know that this is going to result in 1 success and it's going to result in 4 failures, right? Because that's going to be my 5. So 1 success, 4 failures. That's my total of 5 children. But which one could be successful? It could be this one, or this one, or this one, or this one, or this one. There's 5 different ways that I can have that. So all of the different ways look like this: 1 success, 4 failures. But I have to understand that I need to multiply this by 5 because there's 5 different ways it can happen. So that's what would go here for the probability of 1. It's not just as simple as this, right? I need to have that 5 in front because I have to understand there's 5 different ways it can happen. Now let's talk about 2 successes. Well, once again, okay, that's going to look like this: 2 successes, and then that would obviously be 3 failures. So 2 successes, 3 failures. That's easy to understand. But how many different ways can that happen? Well, it could be these 2. Or it could be these 2, 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 or let's see here, it could be these 2 here. Okay, now it's getting confusing. Did I get them all? Did I not get them all? So I need to find a way to tell me how many successes there are. Okay, or how many different ways it can happen is I guess what I mean. I need to find a way to tell me how many different ways it can happen. And this is actually something that you might have learned back in, believe it or not, back in pre-calculus maybe, or maybe even before that you might have learned this. Okay, and to figure out how many different ways it can happen, that's the number that goes out here, I have to really think this through. And this is called combinations, okay? So this is called NCR, meaning combinations, okay? Actually, our book calls it NCK, where we have N trials and we're looking to choose K successes. So N is total trials, and K is successes that we're looking for, okay? And the way we write this is actually mathematically we write N choose K. And we use these big parentheses with the N on top and the K on the bottom. Now what this means is this is saying I have 5 kids, right? I have 5 kids. 5. And I'm choosing 2 of them to be successful, okay? And this is actually how we put it into our calculator, which I will show you in a moment. But the 5 choose 2 is a mathematical way of trying to figure out if you have 5 children, how many ways can you take 2 of them to be successful. Obviously, the other 3 are going to be failure. Now, there is a formula for that, but I first want to show you actually how to use your calculator to find this, because it is very, very simple on your calculator. So pull on your calculator. First thing you're going to do is you're going to type in 5. That's the number of trials. Then you're going to go math. Then you're going to slide over to PRB and go down to NCR. Now remember, our book calls it K, but R just represents successes, whether you call it K, A, B, or Q, or whatever. It doesn't matter. So then you're going to say 5, choose 2. So this is going to tell us how many different ways can you choose 2 out of 5. And there are 10 different ways that you can choose 2 out of 5. So once again, that means that there are 10 ways that I could do this. If we go back to the other one, which we kind of did in our head, we did 5, choose 1, and 5 choose 1 is 5. So that's easy. 5 ways, how many can you choose 1 of them? Well, 5, that's simple. So that's why we knew that first off the top of our head. But for other ones, it gets confusing. Right now, I'm going to give you the formula here. So let me slide over a little bit here, or slide down. I'm trying to find room here. Hold on a second. So the formula for NCR is actually n factorial on top divided by r factorial times n minus r factorial. Now, here's the thing. You really don't have to know how to use that formula. You're never going to be tested over it, at least in this class. I just want you to understand where it comes from. It is kind of a crazy formula using factorials, and if you remember that from pre-calc or not, I don't really care. I need you to be able to use your calculator to do it and understand what you're doing. So 5 choose 2 would be 5 factorial over 2 factorial times 5 minus 2, which is 3 factorial. Don't worry about that. The calculator will calculate it all for you. I just need you to understand why we have to have this. Let's go through as well for 3, right? So 3 would be 3 successes, 0.25 to the third, 2 failures, 0.75 squared, and then in front of this we would have 5, choose 3. We would have to figure out how many different ways that can happen, and that will tell us the total probability for having 3 successes. So again, I'd have to go to my calculator. I'd have to do 5, choose 3, and that tells me there's 10 ways that can happen, times 0.25 raised to the third for 3 successes, times 0.75 raised to the second for my 2 failures, and I get that the probability of exactly 3 successes out of 5 is 8.79%. So this would be 8.79%. Okay, so hopefully you kind of get the idea of this. I'm going to come, sorry about that. I'm going to come way over here and explain this one more time. So, if we have a probability of success P, probability of failure Q, and N trials, okay? If I'm looking for K successes, so I have N and I'm looking for K successes. N trials, K successes. That would be P to the K, because that's how many successes I want. And I would do N minus K failures. Let me give you a quick rundown real quick. Let's say that success is 25%, failure is 75%, and I have 20 trials. And I'm looking for the probability of exactly 7 successes. So I need to figure out how many different ways can I choose 7 successes out of 20. That's what this is going to do for me. You don't need that crazy formula. You could use your calculator. And this tells me that I have 7 successes. And that would obviously mean 13 failures. 20 minus 7 is 13 failures. So I'd have to go to my calculator, and I would say, okay, I have 20, choose 7. And that is how many different, whoa, can you believe that? That's why this gets so complicated. There are 77,520 ways you could choose 7 out of 20. That's a lot. It's crazy. Never would have thought that. But I'm going to multiply that by my 7 successes times my 0.75, or my 13 failures. So my 13 failures. And I get the chance of choosing 7 out of 20 with a 25% chance of success is exactly 11.24%. Okay? So hopefully that makes a little bit more sense. This is like the typical formula that your book will show you. Okay? It'll say that the probability that you have exactly K successes, right? The probability that you randomly have, I guess not randomly, but the probability that you have K out of 20 successes would be that formula right there. Hopefully that makes sense and it's easy to understand, I hope. Okay? So I know I have a lot kind of written here. Let's actually start looking at another problem here to have this make a little bit more sense. I'm actually going to teach you a huge shortcut on your calculator. Okay, so rhubarb is a vegetable that is grown. 5% of rhubarb plants die before they produce any actual rhubarb. Sally buys 12 rhubarb roots to plant. Let X be the random variable of how many rhubarb plants die. So as long as the 5% stays constant, no matter what, I should be good to go here. And I also need each to be independent, which means if one dies, it doesn't affect the next. I do have 12 trials I'm going to look at, and my chance of success is 5%. And you have to understand here, success is dying, so which I know is not necessarily successful, but that's what we're calling it. So there's a 5% chance of success. Failure for us would be 95%. Now again, it's kind of opposite way of thinking here. Success is dying. Failure would be doing good, surviving, and why we call it that. But just understand that that's what we're looking for. We're looking for how many plants will die. Okay, so it says find the probability that exactly 3 plants will die. So we have 12 plants. We want to choose 3 of them to die. I need this first part right here to represent the fact that it could be any 3 of the 12. I don't care. But what I do know is that I'm going to have 3 failures, or 3 successes. Geez, I'm going opposite of what I was just saying. I need 3 successes. I mean 3 to die. 5% chance that 1 dies, so I need 3 of those. And that would mean that I have 12 minus 3 is 9 failures. So I have 3 die, 9 don't die. And then this is going to tell me how many different ways that can happen. So when I go to my calculator, I'm going to do 12, choose 3. And that, what did I type in wrong? Oh, I never typed in the 3. Okay, so 12, choose 3. and that is 220. So I come back here. I have 220 different ways this can happen, but all of them involve 3 successes and 9 failures. Okay, so now I'm just going to go back to my calculator. I'm going to type in 220 times 0.05 raised to the third for my 3 successes times 0.95 raised to the 9. Of course, I would type that wrong. Raised to the 9. Okay, and I get a chance of 1.73%. So there's a 1.73 probability that this happens. 1.73%. Now, I want to teach you a real quick trick on your calculator to how you can have your calculator do all of this math at once. This is pretty cool. So I'm going to go second vars. Okay, second vars. That's your variable button. So second vars. Slide down to, you're going to see, this is where you get normal CDF and all that fun stuff. This is where we see binomial. Now we want exactly. Binomial Pdf means exact, right? I don't know how else to tell you to remember that. Then you just need to know it. P stands for exact. I guess I wish it would be an E for exact. But regardless, Binomial Pdf means you're looking for an exact number. So you first have to type in how many trials you have, so 12. Then you need your comma for success, 0.05. And then you need a comma for exactly how many you want. So this is red, 12 trials, success is 5%, and I'm looking for exactly 3. So this is what Binomial Pdf will do for you. And notice it gives you that answer right away. So let me tell you one more time how that works. I'll write it down here. So it's Binomial Pdf, and you have your trials, N, success P, and then you have your K, how many successes you're looking for. So for me, that was a Binomial Pdf. That was 12 trials. Success is 0.05, and I was looking for exactly 3. So that Binomial Pdf really makes that speed up the process, okay? But I still need you to understand the formula. All right, find the probability of at least 4 die. Now, at least 4, we have to understand what at least 4 means. At least 4 means 4 or more. Now, we have 12, right? We have 12 trials here, 12 plants. So 4 or more means 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11 or 12. Now, let's talk about how crappy that would be. That means I have to do all of this work that I just did up here that many times. I'd have to do 12 choose 4, figure all that out. 12 choose 5, figure all that out. 12 choose 6, figure all that out. 12 choose 7, figure all that out. That's a lot of work. I'd much rather think of the cases that I don't want, meaning the opposite of 4 or more, which would be 3, 2, 1, or none. That would only be 4 calculations as opposed to a lot more. So I'm going to figure out what is 12 choose 3. That is 3 successes, 9 failures. Or 12 choose 2. That is 2 successes and 10 failures. 12 choose 1. That's 1 success and 11 failures. Or one more here, 12 choose 0. That's 0 successes and all 12 failures. So now I agree. It's still 4 things you got to calculate right there. It's not going to take you 5 seconds. It's still going to take a little bit of time, but it's a lot shorter than doing 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11 or 12. So if I find 3, 2, 1, or none, I could calculate that and then do 1 minus that. Okay. Now, how do we shortcut this? Well, 1, we could do a Binomial Pdf for 3, Binomial Pdf for 2, Binomial Pdf for 1, or Binomial Pdf for 0. Add those values together and then do 1 minus that, and I'll be left with 4 or more. But there's even another cheat. Okay, let me teach you about something else. So go to second vars, and we're going to go to Binomial Cdf. Now, the C stands for cumulative. Now, Binomial Cdf will do how many you tell it all the way down to 0. So if I put in here 12 successes 12 trials, excuse me. Probability of success is 0.05, comma, 3. Now when I put that 3 in here, now if I use a Binomial Pdf, that's going to find exactly 3 and 3 alone. But a CDF will do 3 or lower. So it'll do 3, 2, 1, and none all at the same time for you. Pretty convenient. So when I hit enter here, this is going to get me the probability of, once again, 3, 2, 1, or none. Now, once again, I want to find the probability of 4 or more. So I still need to do 1 minus that value. And I can go up there and grab it. By the way, if you're having any issues with, wait a minute here. I need to store this first. I'm going to store that as x, just so I have it, and then I'll do 1 minus x. If you're having any problems with your Binomial PDF or CDF not working like mine is, make sure your stat wizard is off. That will affect things. Stat wizard off. So the chance of 4 or more dying is 0.002236. You might say, wow, that's really, really low. That's 0.22%. So the answer to this question is 0.22%. Why is that so low? Well, think about it. There's only a 5% chance that one of them dies. So having 4 or more die would be pretty rare. If it happened, I would not only be shocked, but I would actually question if I got a truly fair random pile of rhubarb roots, because that should not happen. And in fact, if it did happen, I wouldn't just chalk it up to a miracle. I would want to find out why, because something fishy happened, the fact that I had 4 or more die. So once again, quick recap of the Binomial CDF. Remember, it does the number you tell it or lower. Unfortunately, there is no other binomial shortcut to do higher. It only does lower. So you got to really understand what Binomial CDF does. It does the number you tell it or lower. So if I'm looking for 4 or more, I need to put a 3 in here so it does 3 or less. Okay? So let's figure out this very last problem here. Find the probability that at most 2 die. Let's make sure we understand what at most 2 means. At most means 2 or less. So this means that I have 12 and none of them die, 12 and 1 of them die, 12 and 2 of them die. Once again, this would be no successes, all 12 failures, 1 success, 11 failures, 2 successes, and 10 failures. Now notice how I'm still writing this stuff out at the time, because you need to. You got to show your work. You need to understand how the formula is used. But when you calculate it, I have no problem with you going to your calculator. In fact, for this one, I'm going to go and grab a Binomial CDF. And I went a little too far there. Yeah, be careful. Make sure you always grab the CDF for this. I have 12 trials. Success is 0.05. And I'm going to plug in a 2 here, because once again, Binomial CDF will do the number you tell it 2 or less, meaning 2 or 1 or none. That's exactly what I want, because that's what at most 2 means. So I'll get my answer right away. I don't have to subtract here, because this is what I'm looking for. And I get 98.04%. So my answer is 98.04%. And somebody might question, why is that so high? Once again, they're not supposed to die. It's very rare for one to die in the first place. So I should have 2 or less die. In fact, what's probably most common is none of them die. That's what should happen. None of them should die, but 1 may die or 2 may die. Okay, but it should be very unlikely for 4 or more to die. So make sure you understand, A, how to use the calculator, and lastly, make sure you really understand when you see these phrases at least and at most, and what they mean and how to interpret them. Because if you mess that up, you could really, kind of mess up a problem. Okay, let's work on one kind of final problem here before we kind of wrap everything up. Now, a company that makes USB flash drives knows that 2% are defective. A supply company inspects 10 flash drives out of a shipment of 10,000 flash drives. We're going to count the number of flash drives X that are defective. So, chance of success, 2%. Now, once again, I know I'm saying success is defective, but that's still what you call it. I have 10 in my trial. I'm going to actually inspect 10. So my sample size is 10. Chance of success is 0.02. Chance of failure is 0.98. Now, here's the question. Here's the issue. I have 10,000. 10,000 is not infinite. And if I take 1 out, or 2 out, or 3 out, or take 10 out, every time I take one out, the number goes down of flash drives that are available to be taken. So does that mean that independence is violated here? And this is a major problem we run into, especially when we're doing a problem like this. If you think about it, after I take one flash drive out, there's now 9,999 flash drives, and if that one I took out was defective, now there's one less defective. If I took one out that wasn't defective, and there's still one less that's not defective, so I am technically changing the probability every time I reach in. So how can I still use the binomial model if that 2% is changing because I'm taking flash drives out of a select group? And here we have a really important rule to learn. It's called the 10% condition. Okay? The 10% condition. And this 10% condition is a very, very important rule. And it basically says that if you have a sample size, okay, of capital N, so capital N is my 10,000. Right? And I'm going to take out a sample of that, a small n of 10. As long as you don't take out too many, we could still say that they're independent. We're still allowed to say they're independent and that P stays the same. As long as we don't take out too many. Well, what's too many? 10%. That's the 10% condition. So as long as we're taking out less than 10%, okay, so as long as my sample size is less than or equal to 10% of the population, I'm okay. Yes, I am slowly affecting the number of flash drives, but as long as I'm taking out less than 10%, it's not a big deal. Here's a very simple example to understand this. Imagine I have a small bag of M&Ms and I start taking them out. Well, every time I take one out and eat it, I'm big time changing the chance of getting M&Ms because there's only so many in a bag, and if I take one out, I'm making a major change to that bag. As opposed to an enormous bat, a huge bat at the factory of M&Ms. I'm talking 1 million M&Ms. If you take 10 out, are you really putting a dent in anything? No, it's such a small amount. So as long as we're taking out less than 10%, we're okay to assume that independence is still okay and that our probability of success P will still stay constant. Okay, so as long as you understand that 10% condition, that our sample is less than 10% of the population, we're good to go. Now let's get back to the problem. I want to figure out the number of defective X, the number of defective flash drives. Well, again, could be 0 defective, 1 defective, 2 defective, 3 defective, 4 defective, 5 defective, 6 defective, 7 defective, 8 defective, 9 defective, or I really squeezed this in there. Or there could be 10 defective. Okay? So again, be prepared to answer several questions here. For example, what's the probability that there is exactly 5 defective chips? Now I want you to think about this. This should be a very low number because there should not be very many defective chips. Only 2% are defective. Now the formula is going to look like this. 10, choose 5, and that would be 5 defective or 5 successes and 5 failures. Now remember, I want you to understand that formula, but I'm okay with you grabbing the calculator. Since I'm looking for exactly 5, I'm going to go ahead and grab Binomial Pdf. Well, what did I grab there? That wasn't right. So second vars, I'm going to go and grab Binomial Pdf. Clicking too many times here. Okay, so 10 chips I'm selecting, chance of being defective or successful, 2%, comma, exactly 5. Now when I do a PDF, this is exactly 5. So look at this answer. That's going to be point and then 6 decimals, 6 zeros. So point 1, 2, 3, 4, 5, 6. And a 7289. So very, very low. 7289%. This is extremely small. Actually, I take that back. That's the decimal right there. I'd have to move the decimal twice to change it to a percent. So it'd be 0.0007289%. That's extremely, extremely low. So if this happened, would you be shocked? Yeah, you better believe I'd be shocked. I'd be more than shocked. But we wouldn't chalk it up to a miracle. We would find out why. Like, obviously, these 10 flash drives were probably not independent. I must have gotten a really bad batch. Something is majorly going on here because I wouldn't just randomly have that happen. Okay, let's do one more problem here, where we talk about the probability that I have, let's see here, let's say at least 2. So at least 2 means greater than or equal to 2. At least 2 means 2 or more. So at least 2 defective chips. Now this means 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10. I don't want to do all that work. I'd much rather do 1 minus getting rid of 10, choose 0, which would be 0 successes, 10 failures, or 10, choose 1, that would be 1 success and 9 failures. If I get rid of 0 and 1, I'll be left with 2 or more. Much, much easier. So on my calculator, here's how I'm going to do this. I'm going to do 1 minus a binomial Cdf, 10, comma, 0.02, comma, 1. Now, let me explain. The CDF is going to do 1 or less, meaning 1 or 0. That's why I chose CDF. And then I'm going to do 1 minus this. That way I get the opposite of 1 or 0, which is 2 or more. And I get a probability of 0.0162. So 0.0162, or 1.62%. So there's a 1.62%. I'm going to have at least 2 defective chips, 2 or more. Okay? So hopefully that makes sense. Hopefully that's a really quick rundown there of what's going on here. And one more thing to talk about. One final thing here is, the big question is, in a probability model, what do we expect to happen? So in a probability model, and this is a binomial, what do we expect to happen? What do we expect the number to be, and with what standard deviation? Now, this is so easy. Remember, in a binomial model, all we have is n, our trials, and p, success. Now, we also have q, but q comes for free. Okay, if you know P, you automatically know Q because it's binary. It's either one or the other. So to find out your expected number of successes, you simply do n times P. It's that easy. N times P is your expected number of successes. Standard deviation is a little bit trickier, but still not very hard. It's the square root of n times P times Q. It's that easy. This right here is huge. This is the expected average in the long run of successes and the expected standard deviation of those expected values. So it's n times P and the square root of npq. So let me go over here real quick and show you exactly how this works. So let me clear off some space here. Great eraser tool there. Okay, so let's go back to this. Okay, here we go. So if I said, okay, of those 10 flash drives, how many do you expect to be defective? Well, how many do I expect to be defective is simply 10 times my success rate, which is 10%, or 2%, sorry about that. So it'd be 10 times 0.02 or 0.2. So in the long run, I only expect 0.2 flash drives to be defective. But of course, that number could vary. And that's going to be the square root of 10 times 0.02 times 0.98, n times p times q square root. So 10 times 0.02 times 0.98, I get 0.4427. You may say, why are these numbers so small? Well, remember, I'm not supposed to have very many defective flash drives anyway. So that's pretty much it. That's very, very easy. Let's look over here at our rhubarb problem. I think I'm saying rhubarb, right? Okay, so let's just say, well, okay, out of 12, how many do I expect to die? Well, here I go. My expected value, let me get a color that stands out a little bit more here. Okay, my expected value would be, well, I have 12, times that by 0.05. 12 times 0.05 is I expect 0.6 to actually die, which means in the long run, after many, many, many trials, I would expect the average of 0.6 to die. So if I did 12, and then 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 12, in the long run, after many trials, after many simulations of 12, I'd expect 0.6 to die on average. But of course, that could vary. And let me come over here for this. The standard deviation will be the square root of 12 times 0.05 times 0.95. So that would be the square root of 12 times 0.05 times 0.95. That would be 0.7549. Actually, it's 0.7550 it rounds up to. And that's how much it would deviate by. And let's do this last one here, just so we understand this one more time. Okay, out of 5 kids, how many do I expect to have type O blood? Well, I expect Of the 5 kids, I expect 25% of them to have O blood, so 5 times 0.25 is I expect 1.25 kids in the long run to have type O blood out of 5. And that number could, of course, deviate, and that would be the square root of 5 times 0.25 times 0.75. And that's the square root of 5 times 0.25 times 0.75. Very, very simple, 0.9682. So 0.9682. So those two formulas help us tell us in the long run how many do we expect out of n, and how much do we expect that to deviate. Okay? So hopefully that was a probably not so short, but a nice lesson on the binomial model and what it means to be binomial and how to do binomial model problems.